1, module 2, and what is the name of module 2? Data lakes and distributed storage, if I can remember properly. Session we saw Hadoop from storage point of view. And we saw that Hadoop is not only about the storage, it is also about the processing. And when we associate the word of storage and processing with Hadoop, we mean distributed storage and distributed processing. So I hope everyone is clear till now. Let's reiterate Hadoop. 3 core components: HDFS, that is for storage, 2 the yarn for resource management, and 3 is the MapReduce, that is for distributed processing. By the end of this lecture, you will get a very clear idea on how the how the processing happens in a distributed manner. In the last session, we saw how the data is stored in a distributed manner. Got it? I hope you can remember that we had a 4-node Hadoop cluster in which we had one master node, and to which we call as a name node, and we had 4 slave nodes to which we call data nodes. So here I'm making it again, since we have a 500 MB file. In order to store this file, we make parts of this file, and each part is called a block. And after that, we saw, for example, we have 4 parts of it. This one, and store these parts. For example, we're storing first part here, second part here, third part here, and fourth part here. When these parts travel and land in data nodes, they are called blocks. Okay. And after that, we saw that if we have a file size of, and this is the file size according to 128 MBs of block size. These blocks would be of maximum would be having the maximum size of 128 MBs and minimum size of as per the requirement. For example, in a 500 MBs file, this would be of 128 MB, 128 MB, 128 MB, and 116 MB. I'll write it here. 6 MBs. This would be. Rest all would be 128 MBs. 128 MBs. So I hope you are clear till now. This is a 4 nodes Hadoop cluster. And there was one thing very important to note. When we say 4, this 4 is related to the data nodes. And why do we refer to only data nodes in the specification of cluster? I told you the reason that since these are the entities, or these are the workers which actually work. Name node does not work. It name node does not processes the data. Actually, we are talking about the data. So these data nodes are the only things which process the data. Name node just manages, and it is just for storing the metadata. So I hope all of you are clear till now. Now let us talk about the distributed processing. So I'll write here getting started with the let me tell you one more thing which I planned for today's session. Since we are talking about the data lakes, so first let us complete the storage part of this. Okay, since you know that HDFS is a data lake, HDFS is a data lake, and nowadays cloud is in the game. Cloud is extremely possible, famous. A person which is who is related to data and has no knowledge of cloud is strictly out of the game, is strictly irrelevant to the data domain. So that is why it is very important to learn about the cloud technologies. Since HDFS is a storage part, it stores the data. This is the data lake, and now you know the difference between data lake, data warehouse, and databases. So this is the data lake which stores all kinds of data. Data lake stores all kinds of data, and the alternative for this, alternatives for HDFS in cloud. We are now studying this. So if we have Hadoop cluster plus PySpark, since these are the two things which will process your data. So in this scenario, we will have HDFS plus PySpark. The one thing will store your data and the other thing will process your data. This is when we have Hadoop cluster. But for example, we are moving towards the AWS cloud, Amazon cloud. Then how can we replicate this kind of thing in AWS cloud? We need two things. One thing for storing the data and the other for processing the data. So the alternative of HDFS in AWS is S3, which is called simple storage service. And we can plug and play with Apache Spark, and we can do our work. What's happening here? So the same thing which we are doing in Hadoop cluster, having HDFS as a data lake and PySpark as a data processing engine, we can do the same thing in Amazon cloud, and it has S3 as a data lake and PySpark as the data processing engine. I'll write it here, data lake. So I hope this is clear. Currently, we are not talking about what is Amazon AWS S3. We are not learning it in a full-fledged fashion, but I'm just giving you some idea on that what are the alternatives of HDFS in clouds. Since we could have started with AWS right now, but since these platforms are first of all they're costly, and after that, if we get a free trial of these services, this trial ends very soon. So if we started now, but when we come to the data part, to the cloud part regularly, by that time the subscription of this account would have been finished. So you will not be able to learn it properly. But that is the reason that for now, you just have to take the idea of what is S3. This is the alternative of HDFS in AWS. And when we talk about Azure Cloud, what is the alternative of HDFS? What is the data lake here? So data lake here is ADLS, Azure Data Lake Service Generation 2. Plus, we can use PySpark through Databricks etc. So this is the data lake. So I hope now you are clear that when we talk about a Hadoop cluster, we have HDFS as a data storage or as a data lake. When we talk about AWS cloud, we have S3 as a data lake. And when we talk about Azure cloud, we have ADLS Gen 2 as a data lake. Anybody having any confusion till now? Let me reiterate this. When we are talking about Hadoop cluster, by Hadoop cluster, we mean we have resources, we have compute, we have yarn. This is Hadoop. It has three core components: HDFS for data lake, for data storage, and the data storage is called data lake. Yarn is for resource managers. We will talk about it in module 8 or module 9. MapReduce is for distributed processing. But since we are about to end up with the storage part, so I thought it better to give you idea about these data lake services. And for Google Cloud, so sorry, for Google Cloud, this is GCS, Google Storage Services or Google Cloud Services. Okay, majorly we will be talking around these two clouds. Okay, now there's a very huge difference between HDFS and data lakes on the cloud. What is the difference? The major difference is HDFS is not persistent. I'll tell you what is meant by persistent. HDFS is not persistent. But S3 and ADLS Gen 2 are persistent. Now, what do we actually mean by the persistent? What do we actually mean by the word persistent? Look, when the, for example, take this example. This is the Hadoop cluster, and this is up and running. By the term up and running, what do I mean? The data is stored, and whenever we submit a code, the code is processed and it gives us the output. All the machines are intact, all the machines are running, all the machines have stored data, name node is running, name node is in coordination with these nodes, and all the activities are being happened. So from up and running, I mean this. Okay. For example, we had a 500 MB file, which we stored in this fashion. Got it? Let's take a very simple example. We had a 500 MB file and we need to process it. And what kind of file we had? We need to count the words in the file. Got it? And the file name is file1.txt. For example, this is the file. This is the content of the file. I'll paste it here. This is the content of the file, and this is file 1.txt. Suppose this is a 500 MB file. I'm contradicting myself. Actually, this is not a 500 MB file, but for simplicity, I'm saying that this is a 500 MB file. Got it? And if this is the 500 MB file, how would it be stored? This line would be stored here. This line would be stored here. The other line would be stored here. We make it smaller. File would be stored here. This block, sorry, would be stored here, or part. This is stored here. This is the file which was saved in a distributed manner in Hadoop cluster in 4 nodes. Now we need to count the words. What do I actually mean by the counting the words? I want to know for how many times hello came, for how many times I came, for how many times each the word teach came. Got it? I want to know the frequency of each word. So what would be the final output? We can count it roughly. If I count big 1, 2, 3, 4, 5, the word big comes 5 times. The word teach comes 1 times. The word data 1, 2, 3, 4 the times. So this kind of scenario. Got it? So you consider that we had a 500 MB file and this is the file content of the file, and we need to process this. Okay, when we come to Hadoop cluster, we store the file in this manner. Cluster is running, and this cluster has given us the output. But once the cluster is shut down, the data is lost. This is exactly what we mean by the persistent, not persistent, sorry. What is the actual thing I wanted to say? HDFS is not persistent. Why? Because once the cluster is shut down, the data is lost. Once the cluster is shut down, all the data which we have stored would be gone, would be lost. So this is a very strict drawback of Hadoop. This is a very strict drawback of Hadoop, because look, when we demand a cluster for this kind of file, we will get data nodes, and we will get, look, for each processing we need compute, we need resources. And what are the resources? Resources are storage, memory. Okay, this is the storage. The storage is gone. What about the memory? Memory is also gone. So the very first drawback of Hadoop cluster is that HDFS is not persistent. When the cluster is shut down, the data is lost, and that is not a favorable situation. Most of the times we have data kept somewhere else, and we have processing kept somewhere else. We have different layers. There is a storage layer, there is a processing layer. Most of the times we want to keep processing layer and storage layer on separate places. So if these two are interconnected with each other, once one thing is gone, the other is automatically gone. Got it? So the next drawback is, if storage is gone, sorry, if the storage is gone, if compute is gone, the storage is also gone. This means that data is coupled with compute. This fact has another drawback. And what is that? That drawbacks comes from the cost point of view. Look, there can be some scenarios where we only want to save the data only, and not process it. There can be some scenarios in which we can afford to only save the data and we want to process it at a further time, at a later time. But in HDFS, this is not possible. In HDFS, if we order storage, we will get compute also. And we will have to pay for both. We will have to pay for the both. This is not the case that we only order compute and we will not be charged for the storage. No. If we get one thing, we will automatically get other thing and we will be charged for the both. And this is not the favorable situation for any company or for any institute, because there can be tons of data. For example, there is 1 terabyte data which we only need to save. So what is the point of getting compute in this case? What would be the favorable scenario for us? The favorable scenario for us would be that we only get storage, and at a later time when we want to compute it, we get the storage at that time. But in HDFS or in Hadoop cluster, this is not possible. So this is the main thing, that HDFS is not persistent. When the cluster is shut down, the data, this kind of data which we have stored, is gone. The data is gone. So this is not a favorable scenario for any company. So I hope this is clear. But this is not the case in S3 or ADLS Gen 2. So let me tell you, and ADLS Gen 2 are persistent. What do I actually mean? The data is not lost when the cluster is shut down. And in case of HDF or Hadoop cluster, it would incur us very great cost, because in order to process this file, for example, if this file takes 5 days to compute, we will have to keep this cluster running for 5 days. It will cost huge, but that is not the case in these scenarios. So S3 and ADLS Gen 2 are persistent. The data is not lost when the cluster is shut down. So when you will make your accounts on AWS and Azure, you will see it in a very better way, that in S3 you will store the data and shut down your cluster. The next time when you come, you will see the data is stored. And on top of that data, you will order some machines. For example, you order 16 GB RAM and 4 CPU cores. You attach the file, for example, file.txt, plus you will order what? You will order 16 GB of RAM and 4 CPU cores, and you will compute. But In the case of Hadoop, this is not the case. This is not possible. So I hope this is clear. So let me just summarize it and finalize it. HDFS is not persistent. When the cluster is shut down, the data is lost. And in HDFS, if one thing is gone, the other thing is automatically gone. Data is strictly coupled with compute. And if we order one thing, we automatically get another thing, and we will have to pay for both. That is not a judicial approach. But in the case of S3 and ADLS Gen 2, they are persistent. They have different layers. They have different layers, separate layers indeed. They have separate storage layer, separate compute layer. So the data is not coupled with the compute in these data lakes, which are on the cloud. I hope this is clear. Is everybody clear till now? We move towards the cloud, but HDFS is still in use. It is still in use. I also have some labs. I have labs from IT University, and whenever I log in, the cluster is up and running. Whenever I log in, the cluster is up and running. For me, it has been running for an infinite time, and it will keep on running for an infinite time. And the company which hosts that cluster, it has to keep the cluster running. By any way, they have to keep the cluster running in order to save the data. Otherwise, if by any chance the cluster goes down, everything whichever I have stored, anything which any other person have stored will be gone. So I hope from this discussion you have got an enough idea on what are the drawbacks of Hadoop cluster. So it's all about the distributed storage. Let us take a 1 minute pause. Computation. HDFS has MapReduce. This is two terms. The first is map, and that is mapping. And the other is reducing. In MapReduce, we have two Java codes. One for mapper and the next one for reducer. And what is mapper? What is reducer? Mapper and reducer are the machines. Suppose we have 4 nodes Hadoop cluster, and if I say we have 4 nodes Hadoop cluster, we have this kind of setup where we have one name node, where we have data node 1, data node 2, data node 3, and data node 4. And suppose we are to process this file 1. We need to count the frequency of each word in this file. What is the file? This is the file, and I'll paste it here. Okay. So this is the file. What do we have? We have 4 nodes Hadoop cluster. The first line would be a first block would be stored in data node 1. This would be stored in data node 2. This would be stored in data node 3. This would be data in data node 4. Okay. Now what do we need to do? We need to find the frequency of each word. Frequency of each word. Okay. For distributed computation, we have MapReduce framework, and it consists of 2 tasks. The first task is mapping, and the second task is reducing. What is mapping? It prepares the data for reducers to aggregate, and this is the place which actually does the aggregation. And what do we mean by aggregation? For example, we need to count the frequency of each word. We need to count for how many times this word hello comes. This comes 1 times. So this is the main thing which will give us the output. Like, for example, this would give us the output like hello comma 1. It will say this is the kind of output we will be having. We will be having the output like, for example, here is the next word I comes 2 times, so we would be having I sorry I 2. There is the word teach. There is the word teach. Let's focus on the word big. 1, 2, 3, 4, 5. We will get the output like big 5. So I think you can understand what kind of output we are going to get. Okay. So till now, we have seen that the data is stored in a distributed manner, in this type of manner, and we will get the outputs in this manner. Okay. Now let us see it visually. Then I'll show you in some more appealing manner. For example, now I am the person who needs to, for example, I am the person who needs to process this file. I have this file, and this has been stored in this manner. What will I do? I will write 2 codes. I will write 2 codes. And what 2 codes? I have told you, one for mapper and one for reducer. Okay. And what would these code contain? These codes would contain the logic on how to perform mapping and on how to perform reducing. Okay. So I will be having this code here. I will throw this code here, this code here, this code here, and this code here. The code will go to these machines. There's a very famous kind of riddle in Hadoop, and the riddle is, does the code go to the data, or the data goes to the code? The simple answer is, whatever thing is smaller, it would take less time to travel. So generally, code is of few kbs, therefore the code goes to the data. And where the data is stored? Data is stored on each node. That is why when the client package the code, how the code is sent. For example, any type of code you can imagine. For example, I will say uh, pd dot read underscore csv dot group by for example name dot count. For example, this is the code. This is the code. This code will be packaged, and this code will be thrown to each machine. This will go to this machine, and each of these machines, and the data will be processed on each node where this data is present. Got it? And this thing is called the, let me write it here, data is processed where the data is actually stored, and this is called the principle of data locality. What is the principle of data locality? Data is processed on the node or on the machine where it is stored. So we saw two things in in distributed processing of MapReduce. Number one thing is uh, the code goes to the data, and the data goes to each machine. And why the data goes to each machine? Because generally, uh, why the code goes to each machine, generally the reason is that the code is of just a few kbs and the data is of generally mbs or in gbs. So if the data has to be moved to the code, it would take a lot of time and it would not make sense. So the code goes to the data, and the number two fact is that there is a principle of data locality which is observed. And what is that? The data is processed on the node where it is located. And some other things to note, that MapReduce is a uh, two-phase process. The first phase is of mapping. The second phase is of reducing. So I hope you are clear till now. For example, till now what we have seen, we have a file, we need to process it, we have written a code, and the code is thrown to this code is thrown to each machine. Now what would actually happen on data node 1? Data node 1, the code is since we have this as a machine, and each machine is having resources. This machine has, for example, I'll say data node 1 has storage where it will save the data. Okay, and also the CPU codes or compute through which it will compute the data or process the data. The session might take time, but once we are done with that, you will be having no issue in understanding how the data is processed in a distributed manner. Okay, so data node 1 has two things, storage and compute. How the data will be processed in this node? The code will come here, and the processor of this machine will process the data here. The processor of this machine will process the data here. The processor of data node 2 will process the data here. The processor of data node 3 will process it here. The processor of data node 4 will process the data here. And this is called the principle of data locality. Okay, this is called the principle of data locality. Now, for example, this machine data node 1 gives us a result, and this gives us a result. For example, this says hello is 1, I 1, teach 1, big 1, data 1. Okay, uh, and when we come to this machine, we can say big 1. Each machine is suppose that each machine is giving us the count of each word or frequency of each word. Hello comma 1, I comma 1, teach comma 1, big comma 1, data comma 1. Now here on this machine, big 1 and 1 two times, big comma 2, data comma 1, and comma 1. So I hope you can understand. For example, there are 4 nodes, and for each of the respective node gives us a result, and we will say this result as R1, this result, the result of machine 2, as R2, this as R3, and this as R4. I hope this makes sense. So let me repeat what all we have done till now. We had a 500 MB file. Actually, let me just paste the content of file here. Yes, this is the file. Let me paste it here. This was the file, and this file has been stored here in a distributed manner. Now we have written a code which and this code is just for now mappers. Got it? The first activity I told you is for mappers. What is actually happen right now? This is mapping. This is mapping. The first phase is mapping. Whatever the result is of the phase 1, that is the result of mappers. Okay, now while this is happening, while the data is processed on data node 1, we say that a mapper is running. Let me write it here. While the data is being processed on data node 1, data node 2, data node 3, data node 4, we say that a mapper is running. I'm deliberately making it in caps in order to highlight it. What we say that mapper is running. What is a mapper? Mapper is a machine on which the data is stored. And when we say mapper is running, it means that the data is processed on that machine. And in the terminology of MapReduce, the first phase is mapping. And since this is the first phase, look, this is a local count, not a global count. Each of the processor is giving the count of this node only. This is not the case that the processor of data node 1 is also giving the accumulated or the final output of data node 2 or data node 3. Each processor or each mapper is giving the result of its own data. So these are the local results, and local results are called the mapper results. And whenever this process is being happened, this is called that a mapper is running. Okay, I hope this is clear. We have 4 blocks of a file. Eventually 4 mappers will run, and now you know what do we actually mean by a mapper will run. When a mapper runs, it means the data is being processed on that machine, and that process is also called the principle of data locality. So what do we observe from here? We observe that number of mappers is equal to number of blocks of the file. And how do I defend that? For example, if we had a 1 GB file, we will have 8 blocks. And for 8 blocks, how much mappers we will have? We will have 8 mappers. So please note this relationship, the relationship between mappers and blocks. The mappers will always be equal to the number of blocks of that file. If the file is of 3 GBs, it would be having 24 blocks. And for 24 blocks, we will be having 24 mappers. And what is mapper? Mapper is a process which processes the data in that respective node. Is this clear? We have seen that the file has been stored in this distributed manner. We have written a code. The first code was written for the mappers, and the code has been sent to the machines, and each machine has given us the result R1, R2, R3, R4. Okay. That once each machine gives us the local count or the local frequency, now this is the time to get the final output. And for the final output, the second phase occurs, and that phase is, I'll just put it here, and this becomes the mapping. This is the phase 1, mapping. Order to get the actual output, you remember I told you we will be getting this kind of output, and this is the reducer which will give us the this kind of output. Okay. I think there is one more thing to tell you. Yes, okay. One more thing. What is parallelism? The main thing. Uh, Parallelism. What is parallelism? Parallelism is how many tasks can run at the same time. For example, this is 907. The traditional machines processes, how do they process? They will, if we have 4 tasks from T1 to T4, how will they process? First, they'll process T1. Once this is completed, they'll start T2, then T3, and then T4. But what is parallelism? The parallelism is that all these 4 tasks run at the same time. And this is the distributed computation. This is the parallel processing. Got it? Okay. So what is the parallelism here? How many units of parallelism will we have? We will be having parallelism is always equal to the nodes of the cluster. And remember, we are talking in terms of HDFS or Hadoop. Parallelism is always equal to the nodes of the cluster. So what do we have in this scenario? We have a 4 nodes Hadoop cluster. 4 nodes Hadoop cluster. We have a 4 nodes Hadoop cluster. This means that in this cluster, we can run 4 tasks at the same time. We can run 4 tasks at the same time. And what is a task? Task is a mapper activity. What is a task? Task is the mapper activity. If in this data node 1, the data is being processed, this is task 1. This is task 2. This is task 3. This is task 4. So these all tasks will run at the same time and will give us the output. For example, if in traditional machines, if this task takes 1 minute, this takes 1 minute, this takes 1 minute, takes 1 minute, and this takes 1 minute, they all will take 4 minutes in combined. But when they are run in parallel, they will all take only 1 minute, because at the same time this is happening, this is happening, this is happening, and this is happening. After 1 minute they will give the result. And this is what we actually mean by the parallelism. So 4 node Hadoop cluster means 4 tasks can run in parallel. But what if we have 8 blocks? What is the case if we have 8 blocks? If we have 8 blocks, we will still be having parallelism of 4 units. This means that first the 4 blocks would be processed, and then the next 4 blocks would be processed. So remember this relationship. There is a relationship between nodes and parallelism. The parallelism means that the number of tasks which can run at the same time, and this is always equal to the number of nodes in the cluster we have. And what is mapper? Mapper is actually a task. But how many tasks? But how many mappers will run? This is determined by the blocks of that file. If we have 8 blocks, we will be having 8 mappers. But how many mappers will run at the same time is determined by the parallelism. And what is parallelism? It is equal to the number of nodes. I hope this makes sense. This means we can run 4 tasks at the same time. And if we have 4 blocks, we will be having 4 tasks. And what is a task? Task is a mapper activity. Participants, is it clear? So till now, we have seen a lot of things when it comes to parallel processing, when it comes to distributed processing. So we had reached a stage where we had taken these outputs. So now you know what is meant by map, what is meant by the terms a mapper is running, and now you know better what is the parallelism, and now you know how many mappers will be required. In case of Apache Spark, this is tasks. Task is the smallest unit in which the work is done in Apache Spark, and above that we have stages, and above that we have jobs. So we will talk about those when we come here. But this discussion is extremely important. Why? Because now you are thinking in a distributed perspective. Now you're thinking that what will happen at this node, what will happen at this node, and what will happen at this node. So this is the distributed processing. Distributed processing is not a rocket science, but this takes some time in order to connect with your mind. If it is connected, then you are good to go. Okay. Now, since we have gotten the output, now we will, and this is the local output, we will have to get a global output. So these results, result 1, result 2, result 3, and result 4 are sent to another machine that is called as a reducer. This machine is called a reducer. So note this point, that the local results are sent. What are the local results? The mappers outputs are sent to another machine. By the way, this word another is very vague here. I'll tell you. are sent to another machine where we will get the global output. And what is the global output? This is the final output. Okay. So this R1, R2, R3, sorry, and they will give us the final output. Like, for example, I told you that what kind of final output. For example, we say that this is the final output. Final output. Now look, where is the file? Here is the file. Here is the file. It had some words. What do we needed to do? We need to count the frequency of each word. And what did we do? We wrote two codes. The first code did all of this process, and after that we write one more code, and that code contains the logic that how is this final result has to be computed, and we will get this result. So I hope this makes sense. Is it clear? And there is one thing that I said, that these outputs are sent to another machine. Where did it come from? If I say another machine, this means that we are adding one more machine. Isn't it? But this is not the case. Apparently, this is said as another machine, but this is any, say, data node 3. We pick the data node 3 and store all the outputs here. Is it clear? This is not another machine. This is one of the machines available with us as data nodes. We take this machines as a reducer, and we do the work of reducing at this machine. So the reducer is one of the data nodes which processes the final output. Participants, is it clear? We had a 4 nodes Hadoop cluster. We had a 500 MB file. According to default block size, we had 4 blocks stored in data node 1, data node 2, data node 3, and data node 4. And now we need to process this file. And what do we need to do? We need to find the frequency of each verse. For this, we write two codes. First is the code for mapping. This code is sent to the data nodes, and each data node processes the data by acting on the principle of data locality and gives us the local output. And this process is carried on each node. After that, in order to get the final output, these local outputs are sent to another machine which we call as a reducer, and this reducer is actually not another machine. This is one of the data nodes which has previously carried out the reducing activity, mapping activity. Okay, thing is very important that we write two codes, one for mapper and one for reducer. I hope this is clear. Is anybody confused in anything right now? So that we are looking at the distributed computation or parallel processing or distributed processing. For this, it is necessary that the file is stored in a distributed manner. So we had this file, which we have stored in distributed manner, having 4 blocks. Now what we need to do, suppose this is a 500 MB file, we need to find the frequency of each words. We write two codes. First code is written for the mapping activity, and this code is sent to each machine. Each machine gets this code and acts according to this code. And when it acts according to this code, this gets the local count or local output. And this process is carried out on each of the nodes. So after a certain time, when these all machines are done with the local processing, they give their local outputs. And now for the final output, and why do we need the final output? Because there is the possibility that this word, for example, this hello word might repeat on some other node. Just in the case of big, if we say big one, if we say that this is the final output, is it the right output? No, this is not the right output. This is not the right output because this word big exists on data node 2, data node 3, data node 4. So this does not depict the true picture of our result. And this concept is extremely important when we come to Apache Spark, when we perform group by, when we perform wide transformations. So try to think in a distributed manner that this is not the case that the result of this mapper is the final result. This has to be accumulated at some point in order to get the final output. I hope this is clear. So the results of these mappers go to a machine which is actually one of the data nodes, and that is called the reducer. This receives the next code which we have written for reducing activity. This takes our all the outputs. For example, if we had I'm closing it 8 blocks, so there total 8 mappers would have run. So each mapper would have given us 4 more outputs. I'm pasting them here so that you can get more idea. Got it? So for example, this is the R8. So we would have gotten 8 outputs to the reducer machine, and this reducer machine would have aggregated all of these outputs and given us the output in this fashion. I hope this is clear. Is anybody confused? R3. So where all the results are going? This result is going here. This result is going here. This result is going here. Where will this result go? This result will stay here. Got it?